All right, kiddos. Happy New Year. Welcome back. It's nice to see your smiling faces today. I just wanted to finish this problem from class today. And remember, what we're trying to do is we're trying to find zeros or roots for these polynomial equations, in particular those with degree 2 or higher, right? Because if it's second or first degree, it's pretty straightforward. It gets a little murky, however, when we have a third or higher degree polynomial. So what we talked about today was a tool, an idea. It's called the rational root theorem that can get you a list of potential roots, right? And again, from those potential roots or zeros, we can get factors potentially and break it down. So here's the deal, right? We're trying to figure out when the heck this guy equals 0, right? And right now, as we discussed in class, we can't factor by grouping. It's not of a quadratic form. It's not a difference of cubes, a sum of cubes, difference of squares. So there's really nothing we can do. Okay. What we do have, however, at our disposal is rational root theorem, which says a possible rational roots, if there is any, is or are, possible rational roots will look like this, right? And so they're all the divisors of the constant over all the divisors of the leading coefficient, which is 1, right? So for the rational root theorem, the middle stuff is not important. We just need the last constant and the leading coefficient, right? So the possible rational roots are going to be plus or minus. I've got to get my plus or minus button. Where the heck is that? And plus or minus is right here. And it's going to be all the divisors of 20, which is 1, 2, 4, 5. We did this in class, 10, 20. Divided by, those are all the possible p's, right? All the p's, which are divisors of 20, the constant, over all the q's, which are divisors of the leading coefficient. Now, the nice thing is the leading coefficient is 1, so that's easy schmeezy, right? So all my possible rational roots, have to be in this pool of numbers. And of course, by dividing by 1, it's irrelevant, so you can kind of ignore that. Right? So these are the list of all my possible rational roots. Okay? Now remember, third degree will have 3 roots, zeros, perhaps some repeated, but it will have 3 roots. So I want to find them. So because there are more than 3 numbers here, not all of them will work. So how do you find which ones work? Right? So which ones work? Well, there are 2 ways. Okay? You can plug them in. And if we get 0 at the end, it's a root. Okay? Or we can use synthetic division. Divide synthetically. So I'll show you how to do both. Okay? So let's check 1, right? And I think we did 1 in class. Okay? So is 1 a root or 0? Or does it work? Right? And so I'll check to see if positive 1 works by plugging it in, right? And so what I'm going to do is I'm going to plug 1 in every time I see an x. So the question is, when I plug 1 in for x, I get 1 cubed plus, or minus rather, I'm just plugging in a 1 every time I see an x, 8 times 1 squared plus, 11 times 1 plus 20, right? So all I'm doing is I'm plugging it in, an x for 1 rather, every time I see an x, right? And what I got here is certainly that's not equal to 0, is not equal to 0. Okay. I got 20 plus 11, that's 31, and this here does certainly not add to be negative 31, right? So it's not equal to 0. Therefore, 1 is not a root or 0. Therefore, x equals 1 is not a root or 0, which means x minus 1 is not a factor of the original cubic polynomial. Okay? Let's try negative 1. And to check negative 1, I'm going to use, instead of plugging in, which we could do, I'm going to use synthetic division. So I'm just kind of methodically checking each one of these. I so far kind of got rid of positive 1, but maybe negative 1 works, right? So I'm going to figure that out by using synthetic division. Now remember, the possible root or 0 is the number that goes in the box, right? So what I'm going to do is I'm going to put a -1 in the box. I'll put that line here as best I can on this Microsoft Word. And then I put the leading coefficients and the other coefficients of my original cubic. So there's 1. I'll leave some room. There's a -8. I'll leave some room. There's a +11. I'll leave some room. There's a +20. Right? And then down here, I kind of leave some space. And I'm going to make a little line there. Right? So 1, -8, 11, 20. Right? I'm seeing if -1 is a root, and if -1 is a root, I'll get a 0 remainder, which means x plus 1 would be a factor of this cubic. Right? So I start by bringing the leading coefficient, the 1, this one, down. So down here, not there, but down here comes a 1. And then I multiply -1 times 1. I put that right here. Oops. Right, then I add. -8, -1 gives me -9. Then I multiply. -1 times -9 gives me +9. I add. 11 and 9 gives me 20. Yahoo for school. Because -1 times 20 is -20, which is perfect. And it's perfect because 20 plus -20 is 0. And that's this number in the box here. That's my remainder. Right? So since I have a remainder of 0, right, that's my remainder term, that means that -1 is a root, which also means x plus 1 is a factor. Okay, so here's where that rational root theorem has just helped me. Okay, I only had to check a couple, thankfully, and I just started working through these possible rational roots, and I already got one. So yes, -1 is indeed a root or 0. Okay, now because -1 is a root, that means my original cubic is divisible by x plus 1. So here's what I got so far. So I'm going to rewrite x cubed as x plus 1 because I know -1 is a root, so x plus 1 has to be a factor, times, and then here I have my depressed quadratic polynomial, or at least the coefficients of. So it's going to be 1x squared minus 9x plus 20. Okay? Now, I don't even have to fuss with the rest of this possible rational roots because I've used the rational root theorem to take my cubic down to the product of a linear and depressed quadratic expressions, right? And for quadratic expressions, I don't have to use the rational root theorem. I can factor, or I can set equals 0, use quadratic formula, or I can use completing the square if I'm feeling cheesy. Okay, and I'm going to do that, right? So I'm going back to get my factor hat on and asking myself, is that factorable? And it is. Yahoo! So I got an x here, I got an x there, and I need two numbers that multiply to be 20 and add to be -9. And of course that's -5 and -4. And now I have factored my cubic, the original cubic polynomial, into the product of 3, 1, 2, 3, very nice linear factors, right? And so therefore I now can solve. So therefore my solutions are -1, 5, and 4. Of course 5 and 4 coming from these two factors. Okay? Oop. Now, you could have, if you wanted to, continue to check for 2 and 4 and 5, and you would have eventually, when you hit 4, either by plugging in to the original or to this one, gotten a 0. Same thing with 5. But as far as I'm concerned, once you use it, only use it when necessary, and once I have my depressed quadratic, there's no reason to use the rational root theorem anymore because I know how to deal with this quadratic, either by factoring in this case or setting equal to 0 using quadratic formula or what have you. Okay? So I'll put two problems on the Canvas assignment, both cubics. So I would only use the rational root theorem once to kind of break down your original cubic into a product of a linear and then a depressed quadratic. And then you can work the depressed quadratic as we have in the past. Or not. You can continue also to use a rational root theorem. All right. I'll put those at the bottom of the assignment. Hopefully this video was helpful. Bye-bye.